Hi everyone, welcome to Calculus 2. So what we're going to be working on in this first chapter is going to be chapter 6, where we're looking at these inverse functions. And we're going to be looking at inverse functions more along the lines of transcendental functions as well. That way we can extract what it is to be a derivative or an integral for these transcendental functions. So the very first section that we come across is titled as the chapter, and it's called inverse functions. And what we want to do is we want to start off by defining what an inverse function is. And I'm going to use the same definition that is in algebra, where we have that a function f is called a one-to-one function if it never takes on the same value twice. That is, that is that the output of the function could never be equal to another output of the function whenever x1 is not equal to x2. So this is what we want to highlight at the beginning, dealing with one-to-one functions. And the reason we want to highlight this when we're working with one-to-one functions is that this actually gives us a method, or shall I say a process, or more along the lines of a definition, for us to be able to extract what an inverse function will look like. So using this definition here, this actually leads us into what is known as the horizontal line test. So the horizontal line test this checks, or this tests to see if a function is a one-to-one function. So I'm just going to write here, this checks if a function is one-to-one. Now, what does that mean and how do we work with it? Well, let me give you an example here, or let me give you two examples here. So this is what we're going to do. Let's elongate that. There we are. Alright, so what I'm doing right now is I am creating an axis, x and y axis. That way we can start graphing some functions here, and then we can determine whether they are going to be one-to-one or not. So I have my x and y coordinate system, and I'm going to draw a function here. So in the first grid, I'm going to draw a random function to see if it will be one-to-one or not. So function 1 looks like a parabola opening downward. Function number 2 will look more along the lines of a cubic function. Now, when we use the horizontal line test, we want to determine if that whenever we draw any horizontal line through the function, will it intersect the function more than once? If it does intersect it more than once, well then the function is not one-to-one. If the function only intersects it one time, or if the horizontal line intersects the function only one time anywhere on that graph, then that means, that our function is not a one-to-one function. Now, I've drawn 3 different lines through these functions. The first 3 lines were through the parabola opening downwards. As you can see, the horizontal lines intersect twice. There's only one spot on that parabola where a horizontal line will intersect that horizontal line once. Now, because of that, we have to make sure that we have to extract, by definition, what it is to be a one-to-one function. So we have to make sure that x1 is not equal to x2. And for this particular input, x1 would be equal to x2, which means that the output would be the exact same output, which again violates that one-to-one function. Looking at the x cubed, here we see that for every x input, we always only get one output. And that's exactly what we want to see when we're looking at a one-to-one function. So for the first one, I'm going to say not a one-to-one function. Because again, it does not pass the horizontal line test. Function 2 that I drew here, yes, this is a one-to-one function. Yes, it is a one-to-one function. Now, that is great for us, because now we're going to be able to establish, using this definition, we can streamline that definition into just using that horizontal line test. What I want to do now is I want to develop more of a concrete definition for an inverse function. So what I'm going to say here is let f be a one-to-one function. So again, we're starting with a one-to-one function with domain A and range B. Then its inverse function, we're going to label it as f inverse, has domain B and range A, and is defined by f inverse is equal, f inverse of y is equal to x. If and only if f of x is equal to y for any y in the range B. Okay, so that now gives us a more concrete definition for what it is to be an inverse function. Now, I know it can get a little convoluted, so let's go ahead and let's start breaking it down. If we take a function f of x, and I'm going to break this down for you down here. So if we take a function f of x, let's do this in a different color. So I'm going to take my function f of x, and if this function f of x has a domain of, well, let's say the domain goes from 0, the interval from 0 to infinity, and let's say it has a range from, let's say, -1 to 5, open parenthesis. Then when we talk about the inverse for this function, the inverse for that function, f inverse, what's going to happen here is that the domain for my function f of x now becomes the range for its inverse. So even though I might not be able to, let's say, calculate the range of the inverse function, just by knowing the original function, I'm able to extract what the range should be. Now, same thing holds for the range of my function f of x. Well, if I have the range to be the close parenthesis from -1 to 5, open parenthesis, again, if I cannot calculate the domain for f inverse, that is okay, because from the very beginning I know the range, so when I take its inverse, that range will now become its domain as such. And that's what this definition up here was telling us, that if you have the domain for a function, when you find its inverse, you coincidentally just took that domain and you created its range. Same thing for its range. If you took the range for a function and you found the inverse of that function, then you automatically find the domain of that inverse function. That's how these one-to-one functions work, and that's why we need them to be one-to-one, because anytime that we choose a random x value, we should only be able to get one y value. In this particular case, where we have the first example where we had that downwards open parabola, we can see that we get two y values that are exactly the same for two different x values. And that in itself, if we were to try to find what x value gives us that same y value, we wouldn't be able to know which one it is unless we restrict its domain. That is the beneficial part of having these functions be one-to-one, or in this case, these inverse functions being one-to-one. That way we can track down initially where all of the inputs and outputs are coming from. Great. Now let's extract this a little bit further. So what I want to do here is I want to determine if the function is a one-to-one function. Part A, we're going to have f of x is equal to x to the fourth minus 16. And then part B, we are going to have h of x is equal to 1 plus cosine of x. There we are. So I want you to take some time and try to visualize these functions. Excuse me, for the second function, I forgot to add the restriction where x is bounded between 0 and pi. There we are. That's better. So I want you to try to take a few minutes and try to visualize this. Tap into that college algebra, that trigonometry, or that pre-calculus material where you were taught to graph these functions. Take some time and do that now, please. Pause the video if you need to. I will pause the video as well. Alright, so here we are. Now, I'm going to go ahead and graph these using the software GeoGebra. I went ahead and I have a link for that on Canvas, so if you want to follow along, feel free to do so. You will have to graph these functions yourself there. That way you can get the feel for how GeoGebra operates. So for now, let me go over to GeoGebra, and then we can discuss whether these functions are going to be one-to-one or not. Here we are on GeoGebra. Now, the first function that we're looking at is x to the fourth minus 16. Right away, we can see if we draw a line anywhere on this graph, it will not pass the horizontal line test. So we have to be able to draw that line anywhere on the graph, and it must pass through that graph only once through that horizontal line. So this graph is not a one-to-one function. Now let's look at the other function, which was 1 plus cosine, where it's bounded between 0 and pi. If we look at that function, we here can clearly see that this is a one-to-one function because we can draw a horizontal line at any given point on this graph, and it will only intersect that function once. So, first graph was not a one-to-one function, second graph is. Awesome. Now, we're going to go through back to the whiteboard, and we're going to work on finding the inverse of certain functions. So let's go back. Here we are. So let me just summarize the first part. Yes, f of x is a one-to-one function. Oh, excuse me, I meant no. I am so sorry. No, f of x is not a one-to-one function. There we go. Awesome. This is why I like technology. I can copy and paste, or I can highlight and move as I want to instead of deleting a whole paragraph or sentence. So no, f of x is not a one-to-one function. And if I ask for a justification, then the justification could just be it does not pass the horizontal line test. And then for part B, yes, h of x is a one-to-one function. And again, if I ask for a justification, you could justify this to say that the graph does pass a horizontal line test, therefore the function is a one-to-one function. Very nice. Now, let's see if we can find a formula for the inverse of certain functions. So on these examples here, we want to find a formula for the inverse of the given function. So let's look at this. Part A, we can start off by saying f of x will be equal to 4x minus 1 divided by 2x plus 3. And part B is going to be g of x is equal to 2x squared minus 8x. Now, to do this, to find the inverse of this function, we're going to have to rely on our process from pre-calculus or college algebra or trigonometry or algebra 1 or algebra 2. That process says that the first step that we must do is we need to replace this f of x with a y value. And that's what I'm going to do first. Replace that f of x with a y value. That's step number 1. So I'm going to highlight this as step number 1. Step number 2, we're going to interchange every x and y. Wherever I see a y, I insert an x. Wherever I see an x, I insert a y. Step number 3 is going to be to solve for y. So step number 3, I'm going to say I need to solve for y. Well, in order to do this in this case, what I need to do is I need to multiply by the denominator onto the other side. In other words, cross multiply. So this is going to be x times 2y plus 3 is equal to 4y minus 1. I need to distribute the x. So this is now going to be 2xy plus 3x is equal to 4y minus 1. And in order for me to solve for y, I need to get all of those like terms on the same side. Everything else that does not include a y goes onto its side on its own. So I'm going to have 2xy, move this over, minus 4y, is equal to negative 1 minus 3x. On the left-hand side, I can now factor a y, where factoring a y now leaves me with 2x minus 4 is equal to negative 1 minus 3x. And the whole process to solve for y is so that we can get y by itself. Well, if y is being multiplied by these terms in the parenthesis, then I can divide by whatever's in the parenthesis onto both sides. In that sense, y is now equal to negative 1 minus 3x divided by 2x minus 4. Or you can say that y, if you factor a negative 1 from the numerator, factor a negative 1 from the numerator and send that to the denominator, we actually get 1 plus 3x divided by 4 minus 2x. These two equations are equivalent to one another. One has a few more negatives than the other, which I prefer the one that looks more cleanly. So to find the inverse, the very last step for this is step number 4. Step number 4 is just to replace the y that we solved for with an inverse. So we replace it with an inverse, so this is now f inverse of x, which is equal to the equation that we just found, 1 plus 3x divided by 4 minus 2x. And there you have it. Now there are restrictions to this. For the first part, for the first function, there is a number that does not work within that domain. That number is negative 3/2. So we have to be very, very mindful of that. Same thing for that denominator. Denominator here for this function, we cannot have a denominator of 2, or sorry, an x value of 2. Now we're going to do the same thing for part B. We have to find the inverse of this function. I am going to go through and take the exact same process. Process 1, or shall I say step number 1. Replace g of x with y. So y is equal to 2x squared minus 8x. Step number 2. Replace every x with y and vice versa. So my equation now stands as x is equal to 2y squared minus 8y. I need to solve for y. So I have a few options. Since y is a quadratic, I can complete the square. I can try to use the quadratic formula. any one of those will work here. So we have to be careful, or we have to be mindful of what we use. So I'm going to say here solve for y. So let's get to it. Let's go ahead and let's solve for y. What I want to do in this particular case is I want to divide by 2. That way my leading coefficient here will be 1. So that's where I start. X divided by 2 must now be equal to y squared minus 4y. What I'm going to do is I'm going to complete the square on the right hand side, which means I'm going to take this b coefficient, and what I mean by that is I need to take the coefficient that's multiplying the single variable y, not the one that's multiplying y squared, because we modified that one to be a 1, but instead the y by itself. That's negative 4. So you take that negative 4 and you divide it by 2. Always divide it by 2 because you always want to cut it in half. And you get negative 2. Once you find that negative 2, you square it at all times, which gets us 4. This is the value that we are going to insert onto both sides of this equation. So we get x divided by 2, and I'm going to insert this 4 onto the left side, and I'm also going to insert it onto the right hand side, keeping that equation balanced. On the right hand side, I now get a perfect square. That perfect square factors into y minus 2 quantity squared. On the left hand side, I'm only left with, well, this value, x divided by 2 plus 4. I can modify that to see, or to, let's say, change its look. What I'm going to do here is I'm going to change this 4 to have a denominator of 2. Once I change the 4 to have a denominator of 2, looks like this. Now I add the numerators and I get x plus 8 divided by 2. Very nice. Now what I need to do is I need to keep solving for y. I need to take the square root of both sides. Now it might be easier said than done, but when you take the square root of both sides, I want you to be very, very careful with that. And we want to be careful with that because when we take the square root, we actually get 2 different values. We get positive or negative of that square root. And so we have to be careful and we have to choose the right value, because at the end of the day, remember, quadratics are not one-to-one functions. So we have to make sure that we have a restriction for this. Now, I've realized as I'm coming through and working through this whole problem that at the very beginning there was an initial condition that I absolutely forgot to give you. And to that I apologize. I'm going to say and x is greater than or equal to 2. My apologies. Finding this restriction, we could now go through and we can now say, okay, well, something's happening here where I'm going to be able to choose either a positive or a negative version for this value. Okay, so I want you to follow me along with this. Notice, from the very beginning, we had x was greater than or equal to 2. But what was the second step? The second step was where we interchanged every x with y, which means if we had an initial domain restriction of x is greater than or equal to 2, guess what's going to happen here? Well, what's going to happen here is that this initial restriction coming down here under step number 2, remember step number 2 was where we interchanged. Under step number 2, this now becomes that y needs to be greater than or equal to 2. Okay, so keeping this restriction going for us, we can now start looking at this here, that y is going to be equal to 2, after I add this over, 2 plus or minus the square root of x plus 8 divided by 2. Now from here we can start extracting. Well, what values are we going to be able to choose for this x value so that we satisfy that y is going to be greater than or equal to 2? Or more specifically, what values in here, after we evaluate x plus 8 divided by 2, will get us either positive or negative? Well, for that, we then need to start taking a look at what's going to happen. So I want you to start anticipating. What values we're going to be able to extract from here. Are they going to be positive or are they going to be negative for these y values? Well, what do y values need to be? They need to be greater than or equal to 2. So what happens if we start getting negative values? Well, even if this works, 2 minus some number is going to start getting us possible negative values, which means that those y values are not going to be greater than 2. So we have to be careful with that, in the sense that we only want positive values. Once we're able to get positive values, then we're going to be able to extract all of the values that we are going to need. Awesome. Now, we need to extract finally here what is going to be the domain, that restriction. Okay, so in order to find this restriction, or this domain restriction, we need to go with the radicand. This radicand x plus 8 divided by 2, that's the portion inside of the radical, in other words the radicand, must be greater than or equal to 0 in order for this to work. Well, if I'm in this particular case, if I multiply by 2, I get this, which means that x must be greater than or equal to negative 8. This now says that this domain for your inverse function begins at negative 8 and then increases all the way to infinity. Awesome. So now that we get to see this, we can actually start extracting this a little bit more and more further to work with inverse functions, or more specifically, inverse functions that are one-to-one. So I'm going to go ahead and I'm going to draw a diagram for you. That way we can start extracting what we need in order to start applying calculus to these inverse functions. Okay, so here is a diagram that I have where I have a function here, and this function is f of x. Notice that this function is a one-to-one function. And I also have its inverse function here, which is also a one-to-one function. Now, working with the inverse function, I'm going to identify a point on this graph to be a point AB. Now, the reason I want to find a point on this function, on this inverse function, is so that I can start breaking it down just a little bit more. So what I want to do at this point in time is I want to go ahead and start extracting what it means to have a rate of change for this inverse function at the point for AB. okay, that's going to involve some calculus for us. Well, to find the rate of change, that means we're going to need to take a derivative. Or, better yet, we can find a better or a different definition for it if we start including the tangent line at that given point. Now, remember, the tangent line at that given point, I'm going to call this line, let's say, L1. L1 is tangent to function inverse of x at the point AB. Now, in this particular case, we can go through and we can find the slope of this line, and the slope of this line is going to approximate, in a general sense, or it's going to give us the slope, or in other words, the rate of change for this inverse function at point AB. Now, what is this slope? Well, we can interpret the slope as we saw in Calc 1 as the change in y's and the changes in x. Awesome. So we're going to kind of hold on to that in our back pocket because that's going to play a big role. Now, what I also want to do is I also want to recall what the definition for an inverse function implies. Well, the definition for an inverse function, what that implies, says that if we have an x component and a y component in a function, then when we find its inverse, that domain and that range are then switched. Which means for this given function f of x, because it's the inverse of f inverse of x, I will be able to find some point on this graph that will be b comma a, because they are inverses of one another. That's awesome. And that's awesome for this reason here, that I can go through once again and I can then generate a tangent line for the function f of x at the point BA. And this tangent line I will be able to find the slope of this tangent line at the point BA, and that will then approximate my rate of change. So that's really awesome to see at this time. Now, what does that mean? Well, looking at this piece here, if initially my inverse function had a delta change in x, well, that kind of translates into a y change here, which means instead of having my y's change, I'm going to have my delta x here because of my inverse function. And if my x's are changing, then that means my previous y's are the ones that are changing. Which now tells me that these two functions are intertwined with one another because they are inverses of one another, which is something that we already knew. So what we want to do now is we want to find what is that rate of change for this inverse function at the point AB. Or in other words, we want to find, let me write this a little bit lower. We want to investigate what is the derivative of the inverse function at the given value of a. Well, we know that we can approximate that using calculus here, the changes. We can do change in y divided by the change in x. However, if we follow this through, we can say, or we can modify this to try to extract this rate of change here. Well, how are we going to do that? And let me know if you follow this. I'm going to create a complex fraction. Or in other words, I'm going to divide the numerator and denominator by delta y. If we divide the numerator and denominator by delta y, I arrive at 1 divided by delta x divided by delta y. That's really neat, because now I can actually go through and I can focus on this now. Well, what is delta x over delta y? That's delta x over delta y. Well, that's the rise over the run. In other words, that's a slope, or that's the rate of change for this green function, for f of x, which means this is really here the derivative of the function f of x evaluated at the x coordinate, which is b. Wow, that is looking pretty good. All right, that's not looking too bad. So now I can say from the very beginning, if I wanted to find the rate of change of the inverse function of f at the given value of a, I can really just do 1 divided by the derivative of the initial function evaluated at b. Okay, but we got to keep a few things in mind in order to keep working with this. Okay, one of the things that we have to keep in mind, I'm going to say here, note f of the input. If I take the input of b into this function, I get the output of a. Well, what does that mean when I'm looking at the inverse function? Well, what that means when we're looking at the inverse function, that means that any time that we take any b value, we will get the inverse function evaluated at a. Now, why is that beneficial? Well, that's beneficial because we're not done with this piece. And the reason we're not done here is because this b value now takes on a different form. This b value, or this value for b, now takes on the form of f inverse of a. Which means if we want to find the derivative of f inverse evaluated at a, all we need to do is find 1 divided by the derivative of the function evaluated at the inverse function of a. All right. So I know that is a big spoonful to try to take in. So what I'm going to do is I'm going to summarize this in a theorem, and then we're going to go through and work on a few examples to try to see if we can extract those values. Here we go. Let's summarize this in a theorem. So here is your theorem. And again, in this theorem, we just summarize to say that if f is a one-to-one differentiable function with inverse function f inverse, and f prime of f inverse of a is not equal to 0, then the inverse function is differentiable at a, and f prime of f inverse of a must be equal to f prime of f inverse of a. Okay, so that is huge to try to extract. So what we want to do is we want to then try to use this theorem on a few examples. That way we can get our feet wet in using them and how they're supposed to be used. So what I want to do here is I want to find the derivative of f inverse evaluated at a. And I'm going to give you a few different functions so that we can give those a shot. So here's what we have for the first example. We have that f of x is equal to x cubed plus 3 times sine of x plus 2 cosine of x, where a is equal to 2. So again, our goal is to find out what is the derivative of f inverse of what is the derivative of f inverse evaluated at a. Now, in order to do this, again, we are going to apply the theorem that we learned previously. which means I need to go ahead and I need to find out what is f inverse evaluated at a. So that's the very first step that we need. Now, in order to do this, I am going to go ahead and refer to this diagram up here. Remember what we said in how we were looking at these items. This a value was the input for my f inverse. In other words, it was the output for my function. And this is the key right in here, that a, whatever a we are given, is the output for the function itself that is given to us. So when I'm looking at this function here, what I'm looking for is, when is f of x equal to x cubed plus 3 times sine of x plus 2 cosine of x, when is this equal to 2? Well, we now need to take some time and we need to extract when that's going to happen. There is a really quick view into this. You can start running through some examples for your x values, but be careful. These x values for sine and cosine are their arguments, which means the x values can be anything they want to be because their domain is undefined. We also have x cubed. So my question to you is, what number, when we substitute into x, would make this x cubed go away automatically, and would either make sine or cosine go away when it's evaluated at that x value? And some of you might be saying, well, it could be 0 or pi halves or pi or 3 pi halves. That's my suggestion, is give those a shot. By observation, what happens when we try x is equal to 0? Well, x is equal to 0, this will 0 out. Sine at 0 is 0, so 3 times 0 is 0, so automatically first term is out, second term gone. Third term, what is cosine at 0? Well, cosine at 0, we actually get something real nice. Yeah, we actually get to be 1, which means 2 times 1 is 2, which means we got our answer. So we get f of 0 is equal to 2. Not too bad. All right, I like where this is going. Now that we have this, let's keep going. All right, let's keep going. So remember, I want to get to this part here, and that is where we're going to go. All right, so here we go. I'm going to use the inverse operation on this portion here. So using the inverse operation, this is going to tell me that 0 is equal to the f inverse evaluated at 2. Awesome. This is one of my key aspects here, because I need that. Not only do I need that, what else do I need? I need to find the derivative for my function f. So let's go through and let's find that derivative for the function f. All right, so I'm going to do the derivative right over here. So let's see f prime of x. Let's find that derivative. Taking the derivative of x cubed, this should be a review, which will get 3x squared. The derivative of 3 times sine of x, this should be 3 times cosine of x. And finally, the derivative for 2 cosine of x, this should be negative 2 sine of x. There we are. Not too bad. Not too bad. All right. So now that we have this, we can say, hey, this is one of the important items that we need. So when we're trying to find what is f inverse of a, well, f inverse of a, we know that to be f inverse of 2, which is 0. That means that 0 needs to be evaluated into that derivative. So this is going to be f prime evaluated at 0, because again that was f inverse of a, which was 0. So now that's actually real nice to be 3 times 0 squared plus 3 times cosine at 0 minus 2 times sine at 0. And what do we get? First term goes away, last term goes away. Middle term just turns into 3, which means f prime at 0 is equal to 3. Good. That's not all. We're almost done, but that's not all. So to find, or to say that we found this derivative of this inverse is really saying that we looked at this evaluation, where this was f prime evaluated at 0 by this initial work here, and then f prime evaluated at 0 got us 3, which means this is just 1/3, which means we found our answer, which is just 1/3. Awesome. Yay. Great job so far. Now, let's do example 2. So for example 2, I want to take f of x, and f of x is going to be the square root of x cubed plus 4x plus 4. There we are. Where a is equal to 3. And we're going to take the exact same approach like we did up top. So if you want to pause the video and attempt this on your own, by all means be my guest and press pause on the video and go ahead and do it. I'm going to not press pause on the video because I have my charging cable here. Voila. So again, if you want to take time, go ahead and do so. I'll give you enough time. Alright, spoiler alert, the answer's coming up. So at this point in time, what I want is, I want my function f of x, which is the square root of x cubed plus 4x plus 4, to be equal to the value that is given to us, which is 3. So somehow, some way, I need that radicand to be 9. That way, when I take the square root of 9, I get 3. So in other words, what x value can we input here for that radicand to evaluate to 9? Yes, by observation, x needs to be equal to 1. Nice. Yes, in fact, if x is 1, that's 1 plus 4 plus 4, that's 8, 1, that's going to be 9 squared, 9 is 3. Look at that. Making good headway here. So that's going to be f of 1 is going to get us 3, which then means by the inverse rules, 1 is going to be equal to f inverse of 3. Again, that's the first part that we need. The next part is we need the derivative, f prime of x. Well, in order to get f prime of x, let me not jump the gun here. In order to get f prime of x, I'm going to rewrite my function into x cubed plus 4x plus 4 raised to the power of 1/2. Now, in order to take the derivative, I need to apply the power rule and the chain rule. So let's go through a quick power and chain rule. Drop the exponent forward. Keep the inside the same. Subtract 1 from the exponent. A half minus 1 gets us negative 1/2. Take the derivative of the inside. That's a chain rule. So first we did the power rule. Now we're doing the chain rule. We need to take the derivative of the inside. The derivative of the inside is going to be 3x squared plus 4. Alright, so that's derivative here, derivative second term, and derivative of the last term is just 0, so that goes away. There we are. So let's rewrite this differently. That way we can rewrite it a little bit more cleanly. So my numerator here appears to just be that 3x squared plus 4, and the denominator, the denominator appears to be 2 times the square root of x cubed plus 4x plus 4. There we are. Now, like we were doing before, we now need to then evaluate at this x value. So what is that x value that we chose? Well, that x value that we chose was 1. So let's go ahead and let's evaluate f prime at 1. Well, if that's the case, then this numerator is just going to be 3 plus 4, that's going to be 7. The denominator, that's radicand is 9, so square root of 9 is 3. 3 times 2 is 6. Perfect. And that's the second portion that we need. So let's roll all this into 1, which means that if I wanted to find the derivative of f inverse evaluated at 3, then that means I needed to find 1 divided by the derivative evaluated at f inverse of 3. Okay, but f inverse of 3, we found that first part just to be 1, which means we need to evaluate the derivative at 1, which we did, which is 7/6, which means this is 1 over 7/6. That's a complex fraction. Simplify, which means our answer is 6/7. And there we are. That is your introduction to calculus on the very first day. So we have inverse functions, and now we know how to take their derivatives and evaluate those rates of change at any given value that is given to us. So I hope you all enjoyed this lesson, and I will see you all for the next lesson where we are going to be talking about exponential functions and their derivatives. I'll see you all next time.